Thank you for the organizers for the opportunity to tell you a little bit of my work today. This was done as a sabbatical visitor in Jeff Bader's lab at SIO at UCSD. This is a very broad title, and I'll just be telling you a little story to it. So what I'm going to do is concentrate on just evaluating three components of RNA: the stability of ribose, stability of the nucleobases, and stability of the phosphodiester bond as a function of pH and temperature. My talk will be divided into two sections. First, I will talk about the pH of the early ocean, and I'll concentrate on what happens at high partial pressures of CO2. And then what I'll do is run you through extrapolation of experimental data to model the effect of pH and temperature, again, on those three systems: decomposition of ribose, deamination of cytosine, that's the one I'm going to concentrate on since it's the least stable of the nucleobases, and to look at the hydrolysis of the phosphodiester bond from some experimental information on RNA oligomers. Okay, so first, ocean chemistry. So very, very simple model, just four equilibria. So you've got the four equilibrium constants here, the Henry's law constant for CO2, first and second acid dissociation constants for carbonic acid, and KSP for calcium carbonate. In this case, we're just going to look at calcite. You can take these four equilibrium constants, manipulate it into this equation, which now relates the partial pressure of CO2 with the proton concentration and hence the pH. If you just stick in standard values for these equilibrium constants into this equation, you get this black curve here. So present partial pressures of CO2, about 3.5 times 10 to the minus 4 atmosphere. That corresponds to a pH of 8.3, which is pretty close to the pH of the present ocean. But of course, since we want to sample a wider range of conditions, we need more robust numbers than just these standard condition numbers. Thankfully, somebody else has figured all this out, so I went back to the literature and looked at these papers. So again, these are the expressions for the four equilibrium constants. The A's, the B's, and the C's, those are just constants based on empirical fit. And the two variables here are the temperature and the salinity. Here is one of the plots using those more complicated expressions for the equilibrium constants. So this is for salinity of 35 parts per thousand, close to the salinity of the present ocean. And this is a plot of pCO2 against pH. And what you'll notice now is on the vertical axis, these are much larger pCO2 numbers. And we chose to look at two limits as suggested by Jim Casting in his 1993 paper. So if you're at very high pCO2 levels at 10 bar, and if the ocean is relatively cool, the color coding is blue is cold, red is hot. So that would be correspond to about pH 5.4. At the lower end of 0.1 bar, which is still reasonably high, the pH would be about 6.7. So these are two of the limits that we're going to look at. So I've told you about pH 5.4, I've told you about pH 6.7. Now it's possible that the atmosphere had much lower partial pressures of CO2, as Minik mentioned in an earlier talk. So we're also going to look at pH 8, and we will also consider very acidic pHs, like you'll see in acidic hydrothermal vents like black smokers, or alkaline hydrothermal vents like Lost City, which have an alkaline pH. And thank you to the previous speaker for showing nice pictures of those. So at these 5 different pH values, again, our goal is to look at the stability of three components of RNA: ribose, cytosine, and the phosphodiester bond, and we will look at those range of temperatures. Okay, here's the experimental data. So I'm going to start with the decomposition of ribose. This is data from Stanley Miller's group from '95. And what they did is they used NMR spectroscopy to look at the disappearance of the hydrogen connected to C1. Here's the experimental data. So this is log K, the decomposition rate plotted against PD. pH is just PD minus 0.4. They did this at 4 temperatures, 120 down to 60 degrees C. If you take Arrhenius plots of these, you get these lines. So the original data are the data points that you see here. And what I've done is I've extrapolated to the 5 pH values that I'm interested in looking at. And I show you one of those lines here. That's pH 5. Sorry, that's pH. Oh, that should be pH 3.5. Apparently it doesn't show up here, at least when I'm looking. You can now, with these Arrhenius plots, you can estimate what the half-lives are. So this is just the half-life at 25 degrees C. And what you see here is, well, if you look at the graph, you can see that since this is log K and these are negative numbers, the lower this is, the decomposition rate is slower, so ribose is more stable under acidic conditions. It's less stable under alkaline conditions, but this part of the curve essentially flattens out. So what you see here in this table is longer half-lives at acidic conditions, shorter half-lives at basic conditions, and the reason why pH 8 and pH 10 have the same number is the data only comes up to about PD of 8.4, which is about pH 8, and we just assume that this curve kept on going straight. So that's ribose. Here is nucleobase decomposition, and so this is, again, the rate constant against pH for cytosine, and this experiment is cytosine deamination. So you just look at the shift in lambda max of the UV absorption peak, and what you can see here is that in the intermediate pH range from, say, about 4.5 to 8, at least at all these 4 temperatures, the pH profile is pretty flat. And that is when cytosine is most stable. As you get more acidic or as you get more basic, the rate of decomposition increases. This plot here is from Miller's group in '98, and in fact, this cytosine data, you can see it's the highest of the 4 lines because it's the least stable of the nucleobases. But this data is actually from Garrett and Zhao's paper. What we did was, again, plotted the Arrhenius lines. So we've got log K against 1 over T. This green line here is exactly the same as Miller's line for cytosine, and that represents pH 4.5 to 8, right? This region here where this is pretty flat. Now at pH 3.5 or at pH 10, it's not as flat, and so we had to estimate what those Arrhenius curves look like, and you get 2 decently straight lines. 2 decently straight line curves, I guess I should say. Okay, here's the pH table. So again, because in the middle pH, the regime is pretty flat. Those have the larger half-lives at more acidic or at more alkaline conditions. Those half-lives are lower. So that's cytosine decomposition. The third component we looked at was phosphodiester hydrolysis. The experimental data comes from Lingelati and Mikola in 2007. And what they looked at was this short oligonucleotide. So this oligonucleotide has been designed so that hydrolysis only happens at one base, which is this uracil that's in the middle. For all these other nucleotides, it's methylated at this position so that it only cleaves here. They only have data for 2 different temperatures, so that's at 90 degrees C and at 35 degrees C. They don't have data in this middle range because essentially they were waiting too long for it to hydrolyze. What we did was, we said, well, you know, if you look at this 90 degrees C curve, it looks pretty close to a quadratic fit. So we're just going to assume that 35 degrees C also fits to a quadratic. It looks pretty decent. Now, because there are only curves at 2 different temperatures, all you can do are 2-point Arrhenius plots. That's not great, but that's what you have. And when you do that, this is the table again of pH versus half-life. So again, in the middle, that's where the phosphodiester bond is more stable. As you get more acidic or as you get more basic, the half-life numbers go down. Now, if you were to put all of this into a single chart, so just to orient you, now the vertical axis is log of the half-life. So the taller the bar, the larger the half-life and the more stable. The way this is color-coded, just think litmus paper, red acidic, blue basic. And the 3 tables that I showed you in the 3 previous slides correspond to this column, and this column. So for example, for ribose, it was more stable under acidic conditions, less stable under basic conditions, and it flattens out. For both cytosine deamination and hydrolysis of phosphodiester, it was more stable in the middle, less stable at more extreme acidic or alkaline conditions. The other nice thing about this plot is you can see that each of these columns, so for example, this ribose column looks pretty much like this, and like this, except that as the temperature increases, the half-lives decrease significantly. That's no surprise at all. One useful way to look at the data is to plot the 3 different processes on top of each other. So these are plots of half-lives versus pH. And if you do that, you see that the lowest of the curves, for the most part, is ribose. So of the 3 components that we looked at, ribose is the least stable, except at very acidic or very alkaline conditions, in which case it's the phosphodiester bond that's going to go first. cytosine pretty much stays high up here. The other interesting thing about these curves is if you were to just to follow one of these, any of these graphs, and you say, well, what is the lowest line? So I can follow this orange line. It peaks right about here, and then I follow the blue line. So in fact, if you just look at these three components and you ask what's the average stability, or where's the position of best stability, it's right around here, pH slightly larger than 5, somewhere between 5 and 6, right around 5.5. This peak will shift slightly depending on the temperature, but it's usually in the pH 5 to 6 range. Some conclusions. So today I talked about the stability of these three components, ribose, cytosine, and phosphodiester bond. Examined over a range of pH 3.5 to 10, and I looked at 5 particular values. There's no surprise that the stability decreases with increasing temperature. Ribose is the least stable of the three, except at the more extreme acidic and alkaline conditions, in which case the phosphodiester bond will hydrolyze faster, at least in terms of half-lives. A cooler, early acidic ocean will stabilize all these three components on average. And if you're very acidic or very alkaline and you're at high temperature, that tends to be destabilizing. I'd like to thank the following sources for funding during my sabbatical. UCSD has been very gracious, and I visited several labs over my sabbatical, and Jeff Beda would like to thank the Center for Chemical Evolution at Georgia Tech, which is jointly supported by NSF and the NASA Astrobiology program. Thank you for your attention, and I'll be happy to take questions.